Okay, so the lecture today is going to be divided into two parts. The first part of the lecture, I'm going to talk about neural networks for images, and then I'm going to discuss in detail convolutional neural networks that started the big revolution of deep learning for images and vision. And then in the second part of the course, I'll give an overview of neural networks for images and 3D shapes. So basically, I'm going to give the big picture of this course, the AI graphics. In the first part of the course, we saw the foundations, the mathematical foundations of AI graphics. And then in the second part, we are going to discuss the practice of AI graphics. And so the second part of the lecture today is going to be about that, the big picture about AI graphics. So I will start in this first part discussing convolutional neural networks for images. And what I'm going to say is that first, the fundamentals of convolutional neural networks, the motivation, and what was the big change in machine learning when convolutional neural networks were introduced. And then we are going to discuss in general what convolutional networks are. And then we're going to discuss in detail the components of convolutional neural networks and how that's used for training and for different tasks in computer vision and in graphics for image synthesis and image analysis. And then we are going to finish discussing the main architectures for convolutional neural networks and give a historical perspective how this field evolved and is in a mature state right now. So starting with fundamentals of convolutional networks, before convolutional networks, we had multi-layer perceptrons, and they had this fully connected layers. And the point here is that a multi-layer perceptron is to learn a general function, and is a model that is not specialized for images or signals that have some properties like stationarity and things like that. And then we see that if you apply this to images, let's take this example, have 200 by 200 images, and if you have multi-layer perceptron with hidden units of the same size, it would be 40,000 hidden units. And then, just this fully connected layer will have 2 billion parameters, right? And then although we can learn general functions, for an image is not actually something that's going to be useful because we want to learn features. And in this case, we are looking for spatial correlations with the local properties of parts of the image. And then we want special operator for that. And you have seen here in the course that this operation is the convolution operator. And furthermore, we can say that this neural network fully connected has more capacity than we need, right? And also, it's not practical in terms of usage because it's a waste of resources and even very difficult to use in practice because it's going to take a lot of space to store all these 2 billion parameters, and also to train is going to be computationally very intensive, and the training itself to get a statistical data to do machine learning, we need a lot of training samples. And we are not interested in general data, we are interested in images. And then, came to the introduction of convolutional neural networks. And then the idea is that instead of having this fully connected layer, we are going to have a locally connected layer because we are looking for features in the image and taking notice that the statistics, different parts of the image for the same feature should be the same. So we are thinking about a stationary process that has translation invariance. And if you do this locally connected layer, then we imagine that we are looking to analyze areas of like 10 by 10. And then if you have like a filter size of 10 by 10 and 4,000 hidden units to be the same as in here, but not fully connected, then we just have 4 million parameters, orders of magnitude less. And on top of that, you have advantage to detect features in a very efficient way and exploit the property that you want to analyze features that has translation variance. And we are going to give examples of this. So the key idea of convolutional neural network is that if we use a standard fully connected network to images, the size of the network is going to scale quadratically with the size of the input. And it's not going to take into account the stationarity of the model that we want to use for images. And then what's the solution? The solution is to use the idea of like instead of having a fully connected hidden layer that's going to analyze the whole global data, the image, we have like hidden units that are going to look for a small patch of the input. And this hidden unit is going to share the weights across the whole domain of the image. And if you remember what we have seen in the course before, so this is a filter, right? And then basically the filter is a convolution operator, and this is called this layer that implements this idea is called a convolutional layer. And a network that has a convolutional layers is called a convolutional neural network. And this was introduced in the seminal paper by Jan LeCun, the professor of NYU, in 1998. Right, and then after that, this started the deep learning revolution for images and computer vision. And so, what is the structure of a convolutional network? Besides the convolution, we have like this structure to have like a typical stage of a convolutional network. So a stage is a combination of a convolution filter bank, and then we have two other layers, one for local contrast normalization and rectification, and a pooling layer. So basically, we have here filters that we're going to learn to detect features, and you can imagine like a dictionary that are going to learn properties of the data. And then we want, besides translation invariant, we want also photometric invariance. So they have like this contrast normalization and rectification. And we want to have a hierarchy of features, and then exploit a multi-scale structure of the data. And then we have like this pooling layer. So basically you have like this three layers combined in a typical stage, and we have the data coming in, and these are features that are going to be processed and are going to be transformed in other features by this unity, the stage of a convolutional neural network. In the convolutional neural network itself, the architecture is a deep network that has a sequence of stages, in this example, 3 stages, each containing these 3 layers that performs this transformation of the data to represent features at different levels of hierarchy. And for analysis, usually in the end, we have like a fully connected layers that are going to do for instance, classification or some analysis tasks. But we have also other options exploiting this basic structure that we're going to see further on. So this is evolution of a process of artificial intelligence applied to computer vision. So this structure for deep learning that combines these convolutional layers with analysis layers is conceptually similar to other structures in computer vision, traditional structures in computer vision, where we had like this, features that were analyzed, for instance, with the SIFT, that scaling invariant feature transforms, and some other means to get like a photometric invariance and other things like the k-means and Fisher vectors, and then creating like a multi-resolution structure like a pyramid pooling or pooling. And then in the end, we had like a support vector machines that is equivalent to these fully convolutional layers. And so we can view the convolutional networks as evolution using machine learning of the traditional vision techniques for image analysis, right? And then we are going to see that convolutional networks not only serves for analysis, but also for synthesis. So now we are going to discuss convolutional neural networks in detail. And then we start with a convolutional layer. And we have seen that the main purpose of a convolutional layer is a feature detector, right? And the idea is that detect features by learning filters. And so learns the kernels of the filters to do the right convolution that are going to detect the intended feature that we want to analyze, right? And this is an example. For instance, we have like this filter, so like a 3x3 patch, right? And then the weights Wij are going to be shared across the whole image. And this is a high pass filter that's going to detect transitions, high variations in the vertical domain. So basically it's going to detect vertical edges, right? And then, you see this image, it kind of highlights where all the edges are related to the vertical orientation. And this is learned from images like that. And so if we had another image with like a diagonal edges or horizontal edges, it's going the convolutional neural networks would learn a different type of high pass filter detecting different types of edges. And then if we train a large data set of different images, it's going to learn all the interesting edges and other basic features that exist in that data, right? But in that sense, this is just one filter. And then convolutional neural network has many filters, so it has different channels. And one channel can detect horizontal edges, other vertical edges, and so and so. And so the convolutional neural networks, one layer is going to learn multiple filters at some hierarchical level in terms of semantics, right? And then here we see like how this scheme is very efficient, because if you have like the same example of a 200 by 200 image, and we have 100 filters of size 10 by 10, then we only have like 10,000 parameters. But we are learning 100 different types of features from this data, right? And features that can be anywhere in the image. So to learn these features, we are going to use is a neural network. So we are going to use a neuron, right? And here we are given an example, neural that has the nonlinearities as a ReLU, rectified linear unit, that became very popular after the introduction of convolutional neural networks. And then basically what happened is that we have features that come into the convolutional neural networks, and have a convolutional layer, and then have these filters that are going to be learned. And from that learning, this feature learns to produce features. And so in the layer enters features on one level and produce higher level features in another level. So basically, we can see these feature maps, and this is important as a representation is important for analysis. And so here in this example, you can imagine, so the input of the image is a RGB image of 3 channels, RGB, and then as the network processes the data, we have the different things like edges and so that are going to go through the neural network until the end, right? And subsequently, in this unit, the stage of the convolutional neural network, we have, after the convolutional layer, we have the pooling layer. So the pooling layer basically has a purpose of detecting where the features are within that small patch. And so imagine here that we would like to have to learn edges, and then from edges learn higher level features like an eye, right? And then as we go through the neural network, we have to detect where within the patch there is like the center of the eye, right? And so how can we do this? To kind of assume that we have the right location, the exact location within this patch. So the idea is this pooling layer that actually is going to create a hierarchy of features. And then there are two things that happen in parallel. One thing, as we go this through changing the scale, we are going to look like let's say that we are going to look by 4 by 4 or 2 by 2 images, right? So if you have a filter that's 2 by 2, then have another filter 2 by 2, and then here we have like the end, the final result, right? And so this corresponds to areas in the image, right? And then we have a feature detector that detects like high values because of the nonlinearity, and then the activation function is going to say, well, this is an important part related to that feature, right? And so in this example, we have like for this whole area, the most important one is like this 112. And then the pooling layer going to kind of reduce the scale and then get the highest value and put it here. And then it's going to do this the same. And then at this point here is going to know that the feature is like in this bottom corner, right? And there's a way to kind of combining with activation function, know where that activation came from in the domain of the image. And then there are other ways to do this pooling. You have max pooling, average pooling, L2 pooling over features. But there are basically ways to kind of change the scale, change the resolution, but kind of preserving the important information about features. And we can interpret the pooling relation in the following way. We can imagine that the convolution sort of linearizes a manifold that we are trying to analyze by detecting certain types of features. And then the pooling layer sort of like combines this and gets the features based on the desired training method. Like in this example, imagine that the task is to detect the orientation, left and right, right? And then we have images of this airplane with different orientations, right? And then the convolution layer is going to kind of detect relative orientation and give features related to that. But then when we use the pooling, we kind of combine that and then say, oh, those are the features for left orientation, that is right orientation. And then it goes to a higher level in the convolutional network as a higher level of features and a higher level of semantics, right? And this is also related to what we call receptive fields. Because if you imagine, like at the first layers of the convolutional neural network, we analyze the images, variations, for instance, edges. In the second layer, we analyze corners, and then areas like different patterns. But in the end, what we want to get, we want to identify, for instance, faces or other big structures, and the big structures occupy a large area in the image. So, and this is a hierarchical thing. Like imagine a face. A face has mouth, eyes, nose, and things like that. So the different features that we are going to detect has each feature has a different level. An edge is it corresponds to a small area in the image. It's a variation. But then when you combine different edges, you can have the shape of an eye, the shape of a mouth, and this has to occupy a larger area in the image. And so this is related to the concept of receptive fields, because since we have a deep neural network with these filters, and they applied and changed the resolution, every time you change the resolution, we have the same size of the filter, but corresponds in the original image to a larger area. And so, like in the end, we have a receptive field that's global, that thinks that belongs to the whole image. But at each intermediate level, we analyze areas of different sizes, right? And this is the purpose of the pooling layer, to create this mechanism, right? And then we have the local contrast normalization that gives a different perspective, because like the convolution, we know that it's an operator that it's translation invariant. So any feature at any part of the image is going to be detected the same way by a filter that is a convolution filter. That's a linear and spatial invariant operator, right? But when you're talking about images, or even relation of different detection of feature levels, we have a signal that can have kind of photometric variance. Like we have this photo, and then the illumination has some characteristics. But let's say you want to detect, different features here, and then if you change the contrast or the illumination, we want to detect the same things. So the eye in this image and the eye in that image is the same eye, but the contrast is totally different. So we want something that's also not only translation invariant, but photometric invariant. And then we use this local contrast normalization. That's a very simple operation that you are normalizing within each patch. So for each patch, we kind of take the mean and the variance and normalize the data in this local normalized domain in terms of the values of the range, right? And so this gives a photometric invariance, and basically when we apply the convolutions, we are going to have the same response to signals that has different types of illuminations. And this even has an effect not just for the initial image itself, but for the features also, because we do local contrast normalization across all the features, even at the higher layers of the convolutional neural network. And this, in a way, is a way to do a regularization of the process and improves invariance, improves optimization, and increases sparsity, right? And it's very beneficial, and also computationally is negligible in terms of the computational costs compared to convolutional layer, right? So these are the three main components of a stage of a convolutional neural network. And then with that, we are going to use a convolutional neural network to learn things, either to do analysis or do synthesis based on different methods. Supervised learning, self-supervised learning, generative methods. And then we have to train, and we are going to train more or less in the same way you train a regular neural network, because all these layers that we described are differentiable, and then we can train optimizing using backpropagation. Basically, the scheme for training a convolutional neural network is not different from training another neural networks. So we have like our data, we have n epochs that should cover all the samples of our data, and we do stochastic gradient descent using small mini batches, and we do a forward propagation through the network. Then we do back propagation, and then we update the parameters. And as we update the parameters, we are going to adjust the weights of the filters, and we are going to learn the filters. And in therefore, we are going to learn a sort of like a dictionary of detectors that are going to do analysis and synthesis of the data. And then to validate the training, we do tests, but at the test time, we only run this in forward mode. And because of this whole structure, ConvNets are very efficient and can process larger images at a little cost. And this, was part of the big revolution of deep learning, right? And now, with this fundamentals and understanding how a convolutional neural network operates, I want to give you a historical perspective of how the architecture of the neural networks based on these prototypes for the structure of neural network evolved through time, right? And then we have this timeline, and the main thing, we are this part of machine learning neural networks is like deep learning. And here, in terms of the convolutional neural networks, is the main example of going from shallow to deep, right? And so we started with the seminal work of Jan LeCun, the LeNet, that was in 1998. And as we are going to see, it was a small neural networks because of the time. And then the evolution came with other architectures. That one of the main things was to create architectures that were deeper and deeper and deeper. So after the LeNet in 1998, we had AlexNet in 2012, and then PGG and Google LeNet in 2014, and then ResNet in 2015. And this was really a very fast improvement. And at this point, around 2014 and 2015, the capacity of the neural networks to analyze things was similar to the capacity of a human. And this was like a really impressive the explosion of computer vision with machine learning and deep neural networks. But notice that between 1998 and 2012, we have like this deep learning gap. And why is that? Because at that time in 1998, the conditions for this to really come true and demonstrate all the power of the convolutional neural networks were not in place for two main reasons. One, because the technological aspect didn't have computing power to process all this data, and also because of the way the internet works and data was organized. There was not enough data to train these neural networks. And then from 1998, there was a big evolution in terms of the availability of data, computational power, and new techniques. And after 2012 and 2014 and 2015, this really became available, and then there was this explosion. And then now we're going to see, the characteristics in detail of this different architectures for convolutional neural networks. So start with the LeNet. So the LeNet was proposed by Yann LeCun in 1989 and was the first convolutional networks. And basically it's even simpler than the prototype that we described. So we have like convolutional layers and subsampling layers that basically were like this pooling layers, and in the end we have like a fully connected layer, right? And here we see an image of a letter A that was hand drawing, and then we can see like the patches for the filters, the convolution being applied, and the change of scale by subsampling. And you notice that we start with like a sum number of channels for feature maps, and then this is going to increase, but the size decreases, and in the end we have like this full connections for doing the analysis. And one of the first data sets that Yann could use with this convolutional network was the MNIST data set that became a standard for like demonstrations and testing. And the MNIST is a data set that was like for handwritten digits. And here you see like that being applied to this convolutional network. So we have a digit tree, and then you see like in the first layer, it detects edges in different directions. And then as we go through the network, we detect corners and regions. And in the end, you have the features that are difficult to visualize, but basically they are higher level features that we can analyze in these full connections and give the probability of each digit that come from an image to be digit 1, 2, 3, etc. Right? And this was the beginning of convolutional neural networks. And then came AlexNet in 2012, and basically the AlexNet uses the same model as Yann LeCun 1998 network, but with some difference. First was a bigger model with 8 layers, and more significantly, use much more data, right? Orders of magnitude more data, right? From 10 to the 6th versus 10 to the 3rd, right? And so this makes a big difference. And the second difference is the in terms of computational power. At that time, the graphics process units were like becoming available, and they used 2 GPUs in parallel to do the computations. And then this gave 50,000 50 times speed up in GPU compared to running this on the CPU. And so they could train all this data in a reasonable amount of time, right? And also include other methods for regularization, like dropout and things like this normalization, things like that. And so this AlexNet had like 7 hidden layers and 1 final layer. And so the hidden layers, they had like 650,000 neurons and 60 million parameters, right? And then, you know, this was trained in these 2 GPUs and took some amount of time, but even that, I mean, like was reaching the limits of what's possible at the time. And they wanted to really go to the limits. That's the reason they had to use 2 GPUs. And if you notice here, they had a very clever way to kind of combine 2 networks, one running in 1 GPU and the other running in another GPU. And the connections between these 2 networks are like very sparse. And this was also possible because of the architecture of the convolutional network. So here we see, you know, the detail of the network that here is difficult to see. We have the inputs, and we have like basically that architecture that we discussed: convolution, local contrast normalization, max pooling, convolution, local contrast normalization, max pooling, and then in this final layers we have like 3 convolutions in sequence, 1 max pooling, and in the end 2 fully connected layers, and for the prediction a final linear layer, right? And this gives a total of 60 million parameters, and in terms of megaflops, 800 and almost 850 megaflops, right? And then after, because from LeNet to AlexNet, AlexNet have demonstrated that it was feasible to do, you know, real data learning with machine learning and convolutional networks. And then after that became a specialization of improving the architecture and the models. So then came VGG, and here I have Google LeNet that I'm not going to discuss in the lecture, but basically, you know, they have the same capacity and the same level of results, with the difference that VGG was more elegant and suitable for doing different types of models on top of that. And the main reason is that VGG was a deeper network compared to AlexNet, but had a very simple design, a very regular design. So the design rules for the VGG, basically all the convolutions are filters that are 3 by 3 with stride 1, and all the max pooling, the change of scale, was dyadic change of scale with 2 by 2 max pooling with stride 2. And there's another interesting thing, is that to have sort of have equivalence of the amount of information that's processed by the neural network, after each pool would double the number of channels. So we reduce the resolution by 2, but then we increase the number of channels by 2. And then this gives a balance. And so this regular design was you know, very important to make it useful to do different types of experiments and apply to different applications. So, and you see that compared to the AlexNet, the VGG, they have like 2 versions, the VGG 16 and VGG 19. One 16 layers and the other 19 layers. And the difference is that the structure here is like the 3 first stages they have 2 convolutions in one pool. And the stage 4 and 5, they either have like 3 convolutions or 4 convolutions in a pool. And this will give more power and a deeper network. And so that's an example of how flexible this approach was, right? And that, was used by many subsequent papers for different types of applications. But they couldn't, extend the depth of the network much more than 19. So 19 was more or less the limits of this architecture could reach. And the second big change was ResNet. That's a different kind of architecture, because the ResNet is a residual network. And so a residual network basically is a stack of residual blocks. So this is a new concept. So what is a residual block? So basically it has the same design as VGG, has 2 convolution layers with like a 3x3 filters, and between them you have like ReLU, nonlinearity, and it had incorporated here the max pooling, because like the first block would halve the resolution and then double the number of channels, the same way as the VGG does, but in the middle of the residual block. But there's a new thing that was introduced for the ResNet that makes a total difference. Is the skip connection. So this residual block has a skip connection that you get the data here, and then goes through the convolution, ReLU convolution, but then has this skip connection that goes to the end, and you add, and then you have the ReLU, right? And so this is the architecture. You have like these blocks with skip connections, and it's the same simple design as the VGG, but has this skip connection that makes a residual block. And why that matters? Because basically, although you have the same complexity at layer and have a simple design, this residual block with skip connections would make possible to have a much deeper networks. Like when the ResNet was introduced, they had like first ResNet with 50 layers, then 100 layers, and they could go even further. And then why is that? Why this makes a whole lot of difference? Because basically we are learning a different function. So I call it here the deep residual learning. Because like usually VGG or other networks, they are learning this map H, right? It's a general map. But if you have the convolutional layers, you have like these 2 weight layers to fit this H function. As we go through the network, the different layers of the network, you see that there's a lot of redundancy in the data, right? And then when you put this skip connection, you have like the map of identity here. And then we, instead of trying to learn this H mapping, we are going to fit inside this F mapping. So basically, in the end, when it comes out of this residual block, is the F mapping plus the identity, plus X, right? And then actually, what we are learning here is F, that is H minus X, right? And there are 2 things that you notice here. One is that as we subtract X, we are subtracting things that come from before, and then we are eliminating redundancy. And this has a big effect because we have a network that is learning new things and not taking into account things that we already learned. And also, when you do backpropagation within this structure, the training is much more stable and the gradients behave very well. And the researchers that devised this, they put a kind of a simple logic that if you want to know the identity, these coefficients here shouldn't have any effect because the identity is going to pass through, because of these connections, right? And so that was the main insight that they had. And from that insight, to put this keep connection, they, devised the architecture of the network. And then we can notice that this, after, as a hindsight, the fact that to have a residual network is related to a powerful concept that residual representation in mathematics and in computer science. And there are many examples of this, like this encoding residual vectors, quantizing residual vectors, using residual for in multi-grid to do solving PDEs. And as we have seen in this course, wavelets. So basically, as we subtract, what has already been learned, this is essentially a Laplacian pyramid that is stacking of wavelets. It's equivalent to wavelets, and we see that wavelets in themselves, they are like a basis of the function space. So the ResNet was very successful and could have like a very deep architecture because of this. And this is a very profound mathematical, fact, right? And the ResNet became kind of architecture of choice even today with some variants. But that at that point, the machine learning evolved in other ways to create systems of learning with combining architecture that had like this ResNet blocks inside it, right? And so then it's that point that historically this evolved in many directions. It's useful to look at variants of convolutional neural networks. So what we have discussed so far was the standard convolutional neural network that basically is an analysis neural network. As I was saying, like you have like this layers that are going to detect features. The features have a hierarchy of characteristics with higher and higher level semantics. And for that reason, we can kind of look at from small patches to a big area of the image, and in the end, reason about those structures that occur in an image, and learn about that and do analysis. In the end, we produce metadata saying, for classification, this is an image of a cat or a dog or something like that, right? So this was the first wave of machine learning for image and for vision. But then we have this more complete version of convolutional neural networks. It's a full convolutional network. It's a convolutional neural network that does analysis and synthesis. And we have like here a bottleneck. And here we have to do something new because we discussed how to change the resolution doing convolutions and pooling, right? But then if you want to change resolution the other way, we have to do the inverse of these operations. And so basically we have like a convolutional network and a deconvolutional network. And this is important for some applications because although we want to understand big areas and say, well, like this big area is a face or some part of an object and things like that, we know that there exists there, but we don't have in the end here where it is, right? Because pooling says, well, there is that feature, and that feature is important, but the location is not precise. So to get the location back, or even to do synthesis, we need this second part. that does the inverse, is the convolutional neural network. And this is important for some applications like segmentation, for image generation, for encoding, decoding, and other applications, right? And so basically, we need to introduce the general operations that does a change of resolution. So we had pooling and convolution, but then to do the reverse, we had to do unpooling and the transposed convolution. And when you have that, it's easy to implement this kind of structure, right? And this is the structure that is used for most advanced machine learning applications, so like generative models and different types of high-level analysis, like segmentation and things like that, right? So one example is this, like semantic segmentation. In the semantic segmentation, you have like this image, and you want to say, well, like in this area, you have to segment the image into different types of objects. So here is like a one cow, another cow, and here's the sky, here's the grass. And then, but we want to know that this exists there, but where they are. We want to segment precisely. And then basically, with that structure, we can do this in a very efficient way. Because as you do the analysis, we kind of detect what exists in the image. But then when you do this synthesis, we reconstruct where they are, right? And then we use the different loss functions to get different applications. So as in the case, we use like a per pixel cross entropy, and other applications use different loss functions, right? Okay, so with this, I'm going to stop the recording, then we can talk about evolutionary networks and image applications. So in this second part of the lecture, as I told you in the beginning, we are going to give an overview of AI graphics. And the main point is that how do you use 3D representations with neural networks? Because when we just talk about images and convolutional neural networks, an image is a kind of a, in terms of representation, it's very simple and very uniform. But when you have like 3D scenes and 3D objects, it's not just changing the dimensionality. Basically, we have something that's much more complex in terms of representation. There are many options to do this using neural networks. And then that was what we are going to see from now on until the end of the course. Different types of neural networks with different architecture, but they are kind of specialized for different 3D representations. And we want to make this make sense and be able to work with all of them at the same time, convert from one another, using this, for the right application with the right kind of representation. And so we are going to basically give a whole summary of the course in the second part of the lecture. It's going to be like a trailer of a film, right? So basically, we are going to start discussing representation and neural networks for 3D data. And then we are going to discuss 3D deep learning applications, so what we can do with this representation and this 3D neural networks. And then we are going to discuss two kind of complementary aspects that are dual to each other. One is like we need to train these networks for the context of each application. And for that, we need the data sets and different training platforms. But sometimes, I mean, we don't have enough data, or the data is not in the format that we need. And then for this, we are going to take advantage that we are doing AI graphics. And AI graphics, we can both do synthesis and analysis of data. And then this is the area of inverse 3D graphics, because graphics, you basically use the rendering process to create an image. But then you can use the reverse of the rendering process to analyze an image in the context of a neural network. And then this is going to lead to self-supervised learning methods. So when you have a data set, you use the supervised method, or even unsupervised if you have a lot of data. But when you don't have the data, we can generate the data using inverse graphics, and then you have a self-supervision. And then this is going to be discussed in the last part. Okay. Okay, so starting with 3D representations and networks, basically, I just said that to describe 3D data, we have many possible representations. And not just that, but we have different nature of representation, because we can have a 3D data that is a signal, and you can view as a continuous function. But we can discretize that signal and see as a discrete data and a representation of that continuous function. And also, we can view the description of 3D data either in a way that we call like a extrinsic, because it's a data that is in the ambient space. But we can see from the intrinsic point of view. So just to understand the difference, imagine we have a scene, a 3D scene, and then you have a function of the whole space. And so this is a extrinsic representation. But then within that scene, you have like a surface. And then you can describe that function immersed in the ambient space. And so have like a extrinsic representation. But then you can define and describe the function that describes this surface, only considering the functions without the regarding of that where that surface is in space. So that would be like an intrinsic description. So just to summarize, we have like many representations. We have continuous descriptions that in general are extrinsic and are given by implicit functions. And then we have like discrete descriptions that could be either extrinsic or intrinsic. And then the extrinsic are discretization of global functions, like RGBD, that would be like the space of a camera, and then volumetric, the space of the whole scene, right? And then you have intrinsic, that would be like the objects, the surface of a mesh, or like the samples for an object, like a point cloud, right? So these 5 types of representations are going to be used in AI graphics, and we are going to discuss them each one now. So starting with a continuous representation, we have seen that this would be like implicit functions. So implicit functions is a function of the whole space, and is a continuous 3D has only implicit functions as a representation. And so implicit representation of a surface, what it is, basically is a function that classifies points related to the ambient space. So we have a surface here, like that bunny, and then you have like this the surface, this contour. We have points that are inside the bunny, outside the bunny, and points that are on the surface. And so this implicit representation can be what's called a sign distance function. So if we take a point in the space and the value of the function is negative, is inside the object. If it's positive, is outside the object. And if it's 0, is exactly in the surface that separates the inside from the outside, right? So this is an implicit representation. So it's given by a function, and the surface is the set of points where that function takes a value 0, right? and is extrinsic because it points in the ambient space, the whole space. And naturally, we represent this by a coordinate neural network because basically we are analyzing whether a function belongs to the object, is inside the object, and things like that. So it naturally that's what we are going to give to this neural network is the coordinate of the function. So it's called the coordinate neural network. And in this case, it's not convolution. This is a fully connected multi-layer perceptron. It is actually a new area of research, this kind of multi-layer perception that are used for coordinate-based neural networks, right? And this is something that started around 2019 with 3 papers coming at the same time in this conference CVPR, and that became, like an area of research and study of, a continuous description of 3D objects using these functions, which called like a implicit neural fields, implicit neural representations, right? And then we have like a discrete representations, and usually discrete representation is based on like some function that you discretize. You have the data, and that data is going to be analyzed by the neural network. And here comes the crux and the source of all the difficulties that we have in AI graphics, but also the opportunities that you can take advantage, because we have this fact that basically you have a representation issue, because discrete 3D representations are plenty. The discrete versions of 3D objects, they have many representations, and they can be either extrinsic or intrinsic that have different characteristics. So usually the extrinsic representations, they come in the form of regular grids. And the intrinsic representations, they exploit the geometry because they are intrinsic and they are irregular. So the extrinsic are representations that are related to images and related to grids. So we have like RGB images, RGBD images, multi-view RGB images. And then we have the 3D version, like a 3D image, a volumetric grid. And this, for this, we are going to use convolutional neural networks and things like that with some adaptations. And then the intrinsic, they are irregular data, and then they are either point clouds, we have just geometry, or polygonal meshes. So that we have the geometry and topology of surfaces. And so let's see them. So starting with discrete extrinsic, we have basically this grids in 2 and 3D, right? They are, and they can have just images, but images with geometry and volumetric descriptions, right? And the good thing here is that we can directly apply convolution and use the architecture of convolutional neural networks for these representations. But it has all the challenges that we have to overcome to fully exploit this kind of data, right? And this historically was a natural extension after, machine learning for images. Then when people started using machine learning for 3D data, they started with RGBD images, then volumetric data and things like that, right? And basically here we are going to use what we have seen in the first part of the lecture. We used convolution as the building block for learning, analyzing, and even generating. And when we extend this to RGBD, we have the visual attributes like color, but then you have geometry like the depth. So be like geometry from the point of view of the camera. And then we have basically two convolutional neural networks that process these two types of data, but in the end, we can merge them for the purpose of analysis or other things, right? And here we use 2D convolutions. When we send this to 3D data, like be a kind of a 3D image, then we can do this either for data analysis or for data synthesis. And then basically you have a convolution, that's a 3D convolution that is going to use a 4D kernel. And it's more or less the same, but as you imagine, this has a curse of dimensionality, because instead of like a square, to be cubic, right? And then if you spend the dimensions like instead of like my image of like a 200 square would be like a 200 cubed, and so exponential in size and also in terms of computation, right? And it's the same for data synthesis, but here we are going to use that same concept as we have seen for the full convolutional neural network, that we have like convolution and the convolution with for the kernel. What is interesting here is that like if you have like a generative deconvolutional neural network for data synthesis, we can have the code for an object, and the network learns to generate an object like a chair based on this code, right? But usually what's going to happen is that we will combine analysis with synthesis, and we are going to train with a full convolution 3D network. And we are going to see this in detail and further on in the course. So now going to the discrete intrinsic data. Here we are not going to think about convolution in the same way we have seen. We have to take into account that the representation is still discrete, but it's not regular, and then this makes a whole lot of difference. And so basically, we have representations that we cannot directly apply convolution. We can indirectly, you are going to see this. And the representations are either a point cloud or a polygonal mesh, right? The simplest is a point cloud. So the point cloud is basically a set of unordered points. And because it's a set of unordered points, there's another invariance that we need to respect. Because if we change the order of the points, if the points are unordered, this shouldn't matter, right? And so the network should preserve permutation, because any permutation we do with the points, the network has to get the same result. And to introduce this is another kind of operator. The same way the convolution preserved translation invariant, you want an operator that preserves permutation. And for point clouds, this is very important. Otherwise, the network doesn't learn anything meaningful. And also, we need a spatial transformation invariance, not just translation, but general transformation. Because if you apply like a rigid motion to all the points, so we need to get the same results. Because let's say we have points that belong to a surface, and that surface moves in the space. But this is intrinsic description. So the fact that the points move should be irrelevant for the network. And so there's one kind of network for that, actually two, PointNet and PointNet++, that we are going to study further in the course. But basically, is a network that incorporates this invariance. Here is a block that guarantees the transformation invariance, and this is a block that guarantees the permutation invariance. And doing that, we have a very effective architecture for point clouds. And then you have polygonal meshes. So can you imagine that a polygonal mesh is basically a point set that we put connectivity, we put topology, and then we don't have just samples of points that lie in a surface. We have the surface itself as a continuous thing. But because it's a polygonal mesh, it's a piecewise linear version of the surface. If the surface is smooth, we are discretizing the geometry in terms of piecewise linear elements, either triangles or quadrilaterals, right? And in that sense, the data that we are analyzing is data that lies on the surface. And we are going to associate the value of this data, like colors and things like that, to the vertices of the mesh. But then we can interpolate those attributes across the elements, across the triangles or the quadrilaterals. And then, coordinates and features are functions that are intrinsic. They are defined on the surface. And we store those values at the nodes, at the vertices, and we interpolate them. And in terms of data structure in a neural network, we can imagine that we are not dealing with a point set. We are dealing with a graph because we have the points, but we have that are nodes in the graph. And then you have the edges that are connections that connect different points. And connects in a two-dimensional way because you connect like 3 points to create a face. And then we glue one face into another face. And then you have to take all this into account, right? The guys that are taking Daniel's course, geometry processing, know all about this, right? Then, how do you do a neural network for a graph, for a mesh? We can try to do a convolution. We can call like a graph convolution. But notice that we don't have translation invariance because as we move through the surface, the connectivity of the mesh changes because, like at this point, you can have like a vertex that has a values 5. And here you have one that has values 7. And then this is not going to be the same filter. It's going to be a different kind of filter. And that therefore is not translating invariant because you cannot just translate the filter because the topology doesn't allow you to do that, right? So, but you can do a sort of operation that we call graph convolution that doesn't have the property of translation invariant, and you have to take this into account. If we really want to do like the mathematically correct operation for convolution, that's translation invariant, we have to do this in spectral domain. So basically, you imagine that in this mesh, we have a function space, and this function space you can analyze, spatially or in the frequency domain. And so we can do a spectral analysis of the mesh and define the convolution there. And that will be the equivalent to use convolution for images the way we have talked in the course before. And we are going to discuss this further when we analyze neural network for meshes. Okay, now it comes to a point to, we have all these networks, all these representations, and we want to do applications, like 3D deep learning for AI graphics, and what kind of applications are interesting. So we have like 3D deep learning tasks, and we can divide into analysis and synthesis. And here are the prototypical tasks that we want to solve. Like we can do classification, segmentation and detection, the same way you did for images, we have to do to any kind of 3D data. And also synthesis, we have to do generate images, shapes, scenes, and things like that. We can do reconstruction. This second part, stereo reconstruction, multi-view 3D reconstruction, is important because it connects images with 3D objects. Because basically, stereo reconstruction and 3D reconstruction, we take images and from a 3D world and create models of this 3D world. We can go back and forth, right? So all these tasks can be combined into AI graphics for different sophisticated applications, right? And so here is examples. So like for classifications, we can use like a multi-view RGB data. So here we have the image themselves, but also we have the information about the cameras that took those images from a 3D object. And then for each view, we have an image in the camera position, and then we can have a convolutional neural network that are going to operate on that image. But after that, that will be the multi-view part, we do like this view pooling and combine all the views into one representation. And then we have like a second stage. It's a convolutional network that are going to operate on shape descriptors. And then, for instance, for classification, it's going to look at several images of the share and say, well, like this is a share with probability 90%, something like that. Right? Another more sophisticated operation is segmentation. And here is a segmentation that's slightly different from images, because we assume that for training, we have a mesh, and we are going to separate the mesh into the different parts, right? Have the wings of the airplane, the body of the airplane, and the stabilizers and things like that, right? And so this is marked for supervised learning. And then we have different views of this mesh, but we also know within the image the identity of the triangles. Like, let's say we color in different ways. Each color is the identity of one part. Like the the wing is blue and so and so. And then from this we have like shaded images. We have depth images, geometry. We have the reference to the surface, the identity of the triangles, and then we can combine this with a convolutional neural network that are going to label different parts of the images. And we do this projection to have a confidence map what that part comes from. And with this, we can have like this training that we have the 3D object that generates those images, and the segmentation on the image of the object. And then with this, the application learns when it looks at an airplane, it trains with different types of airplane to detect what is a wing, what is the body, and things like that. Right? The fact that we have the 3D data in the form of a mesh in the image of that object, we can exploit this for after we train the network to segment real planes, because we know the shape of the wing and things like that, right? And then we have either higher level of analysis operators that would be like a detection and segmentation, because we can detect the same way we detect objects in an image, can detect objects in a scene or in an image that represents a scene. So we have as an input different types of representations, and then as output is going to give the bounding box of some objects, like the bounding box of a chair, the bounding box of a table, and then so we know where things are in space, right? But we can also do a much finer detection, because we can detect and segment the shape of the object. So not only say this is a chair, but we have the points that belong to that chair, right? And even further, we can, for the chair, segment that into parts that would be more or less like applying this kind of algorithm. And so having all this, we have a series of tasks to do analysis of 3D scenes in a complete way, right? And this can combine 3D representation in images in very different fashions. And we are going to discuss this further in the course. And now we have also not just analysis, but synthesis. So we have 3D geometry generation. And for 3D geometry generation, there are many options. Like we can generate a 3D object from a single image, because we kind of know that looking at the image, that object is like a table, and we know that's just for the front of the table, we know the shape of the table, and create a 3D version of the table. Or we can have like a geometry that was damaged, like some part of an object that has holes and things like that. And then we can do shape completion, because we look at this and say, well, like this is part of a share, and then I'm going to complete what's missing. So these are two different types of conditional generation. This one is conditional on an image, and this one is conditional of parts of an object. And then you have like a free generation that we basically, I've shown this before, related to 3D geometry, volumetric synthesis, that you can have a code, a latent code. That's the code that represents an object. And then you have a network that basically generates that object from that code. And interesting thing about this is that because the space of objects is a kind of a continuous space, a probability distribution of certain classes of objects, we can interpolate those codes. And as we interpolate, depending on the structure of the space, we get very nice results, because like here we learned airplanes, right? And then we have like this type of airplane, that type of airplane. And if we interpolate the code, we change from this one to that one to that one in a gradual way. So the wings change smoothly, and the body changes smoothly. And it's very important that combines design with analysis and with synthesis. And finally, we have the part of reconstruction. So reconstruction, we start with images, and then reconstruct 3D objects that came from the images that were like taken from a 3D scene, right? And the simplest is like stereo reconstruction. We have been discussed this previously in the course. We can create a neural network that's going to learn to do stereo reconstructions, be like a stereo machine. So we, to train this, we have like a image of a 3D object. We have an image encoder. We do an unprojection that is mapping from the image to 3D if we know the camera, and then we combine this with a special kind of pooling to have a fused 3D grid, and we do reasoning with this 3D grid and have a final grid. In that case, it's a volumetric representation. So all of this can be based on convolutions, and then you have like the Opus grid of this car, for instance. And then interesting thing about this stereo reconstruction is that follows the classic stereo pipeline that we discussed with projected geometry, but the geometry is integrated into the network architecture, right? And then you have the general multi-view 3D reconstruction that also follows the multi-view geometry that we discussed, that's physics-based and comes from the traditional 3D vision, but includes learning. And then we basically learn things that are difficult to solve if we don't have all the conditions for the traditional 3D vision multi-view geometry. And this is very powerful, and this actually is the state of the art in research for AI graphics right now. Okay. With this, now we come to the final part where we discuss how to train these networks. And to train these networks and to do these applications, we need data sets that has, each data set must have the right kind of data. And we have to create platforms that are going to benefit from this data set for different types of applications. And over the time, this evolved very much. I'm going to just describe the basics to give you examples. We have like for supervised 3D learning, we have data sets for 3D scenes and other kinds of data sets. In the course page, in the course portal, we have like many examples for both 3D scenes data sets, RGB data sets, and all other kinds of data sets. But I'm going just to single out the ShapeNet and ScanNet, noticing that there are many others that you can look, to see more information. And so the ShapeNet is a large-scale data set for synthetic objects, and then afterwards they were combined with the other data set I'm going to show to create the model nets that would be like a very big data set. And this was developed around 2015, and now nowadays, I mean, like we have many others, right? And the other type of data set is this a ScanNet, that as opposed to this is just for synthetic objects. The ScanNet is a large-scale data set for scanned real scenes. So this one, notice that the data set is not just the scans, it's the annotation. So it has like 2.5 million views in 1,500 RGB scans, and has the 3D camera poses, has the surface reconstructions, and also have instance level semantic segmentation. So here we have all the data that you can use to train those applications, right? And there are other specialized data sets for different types of applications. For instance, for motion capture, that is animation applications, and for like outdoor scenes and buildings and things like that, right? But this gives an example, and this was developed like to 2017, right? Yes.
Are those surfaces generated surfaces, or are they somehow measured from the actual object?
Well, this one is like using like a scanner, right? And so the scanner, you have like laser scans, you have lidars, and then but the issue is that I mean, like it's not just to scan the scene. You have, after you scan, you have to do a post processing to put all this metadata. Otherwise, I mean, like it has limited value, right? And that's the problem. And then comes to inverse 3D graphics, because this is very costly, and sometimes the situations just cannot do it, right? And then you can take advantage of inverse 3D graphics and combine this with multi-view reconstruction and learning, and gives a very powerful framework to do high-level AI graphics, something that is only possible for AI graphics. It's difficult to do this in other areas, right? Because here we have rendering, and then you can do self-supervised 3D learning. Take advantage of rendering, because you can put rendering in the loop, and you can use differentiable rendering to learn using back propagation. Because if rendering is differentiable, we can use the regular learning process using back propagation. And then rendering is incorporated in the whole system. And the seminal work with this started around 2019. So these are three different differentiable rendering systems that were used in AI graphics for self-supervised 3D learning. And basically what it means to have rendering in the loop? Well, we have images that are produced from a model. And the model consists of cameras, consists of objects, consists of the properties, visual properties of those objects. And we use this image formation models that basically simulates what a camera does. A camera has a geometry, and then you have like we're going to see this for the course, the rendering equation that basically simulates illumination and how the pleionopic function is constructed from the interaction of light and matter, right? And then you have like this image formation view transformation that are known functions that we can use to do synthesis and analysis forward and inverse rendering. And so and then we can create like this kind of network architecture, because we have like here, see, we have an encoder and a decoder, and in the middle we have the parameters that we want to learn, right? And we are going to learn from images. And so if you have an encoder, this neural network has to look at this image and encode the parameters of the scene. But then if you want to do self-supervised learning, we want to be able to, from those parameters, generate with a render an image that is the same as that, and we compare that image, that's the real image, with the image that came from the model. And when these are the same, the system has learned, right? And for that, we need to do backpropagation both from this side, from that side. To do backpropagation from the neural network, we know how to do it, right? But to do backpropagation from the render side, the render has to be differentiable. And just for illustration, we could apply this in the problem of multi-view real reconstruction. Because imagine that we know the cameras, right? But we don't know the objects. And so in this kind of thing, we know cameras and transformations, but we don't know the geometry and the light. And then we take real pictures, right? And then from those cameras, we try to generate in a rendering system images of objects that should be in the scene, right? And if you can do that, we learn the geometry. And this is actually a very hot topic. You know, nerves, neural radiance fields is done in that way, right? And as I was saying, I mean, like the crux here is the rendering, because like usually transformation, cameras, lights, material, geometry, they are naturally differentiable. But when you put all this together in a render, it's not guaranteed that it's differentiable. And then we have like different ways to kind of make sure that the render is differentiable and combining this. So a differentiable render has to take into account lighting, shading, rasterization, projection, and make sure that all those operations, you can compute gradients and then use those gradients for learning, right? And we are going to see this in the final part of the course. All right, so with this, I'll end and then we have questions.